All right, we're going to find a series solution where the series is going to be centered at some point. Let's just say 0. Okay, so we know that we're looking generically for a solution where we have a sum, our function being represented by a series. We have some unknown coefficients, functions then x minus the center x naught to the power n. So for our purposes, since the center is 0, we just get, all right, we then differentiate twice, and we assume that we can just go ahead and differentiate term by term, differentiating with respect to x, of course. So we can note that when n is 0, because we have an n over here, the first term of our series is 0. So if we need to, if we want to, we could start this series at n equals 1, because the first, when n is 0, the term in our sum is 0 anyway. And similarly, here for n equals 0 and n equals 1, these guys make the terms 0. So if we want to, if we need to, we can start the index at either 1 or 2. All right, so now we're going to plug this into our series. Now, so we have y double prime. I'm going to use this. We'll see why. That's y double prime. And then we have y prime times x. So I'm going to use, I'm not sure which one to use, so I'll use this one, I think, because we're going to multiply that by x. So if you'd like x times y prime, you can write as the sum as n goes from 0 to infinity, and then plus y, 2 times y. Okay, and that's, of course, equal to 0. And now what we want to do is combine these 3 series into a single series. But in order to do that, all the powers of x must be like, right? So let's say we want x to the n. This is not x to the n. So that's a problem. So we're going to shift indices. I guess I'll do this kind of slowly. I'm just going to let, right, so we want to replace n with, let's say, k plus 2, right? Let's see why. So replace everywhere you see an n, we can say that it's equal to k plus 2. And also, of course, when n is infinity, so is k at the upper bound, so that's not a problem. So it's still infinity. And then we have k plus 2. N is k plus 2. This will become k plus 1. This becomes x to the k. And then subtract this over, and we get that k goes from 0 to infinity. Okay, and then we're just going to let, because this is, it's just a k and n are just, if you like, dummy variables, variables of summation. So you can name them whatever you want. So we're just going to rename k as n, right? It's just a name. And I typically don't do this intermediate step of letting n equal k plus 2. I just stick with the letter n or something. So any place we see a k, we can replace it with an n. And then I'm going to go ahead and just bring this down as well. That's all equal to 0. So now you see that all the powers of x are like x to the n, and all the indices of summation start exactly the same place, n equals 0. So now we're free to combine this into a single sum, a big sum, as n goes from 0 to infinity, and then we can get all the coefficients here. Check. 1, 2. Check. Okay. And then, so that was this. Yeah. Next, we have this. And finally, 2 times a. Did I miss something? Oh, okay. So I apologize, but I forgot that there's an n here, right? So let's see. There's an n over here. I'll just put it here. I forgot. My bad. Please forgive me. And then, of course, x to the power n is just a common factor there. And so this is the coefficient for x to the n, and that's equal to 0. And we know that for this series to be equal to 0 for all x's, the coefficients have to be all 0. The coefficients for the x to the n terms. So this means that we can set that equal to 0, which gives us a recurrence. A recurrence relation between the a sub n's. That is to say, we're able to define one of the terms in the sequence, right, in terms of the preceding terms. So that has to be set. So I'm going to look to the highest indexed term and get it isolated on one side and bring all the lower indexed terms of the sequence to the other side. So that's just a little bit of algebra. And so we do have a cancellation. And this is good for all n's at least 0, right? Now what I'm going to do is I'm going to shift indices again. I'm just going to say that this is essentially replace n with n or k minus 2 if you'd like. Again, I'll do this more deliberately. I typically don't use an intermediate index here, so let n equal k minus 2, so you get a sub k. Now the reason I'm doing this is just easier for me to look at. I'm trying to solve this recurrence if at all possible. And this is good for all k's greater than 2. And again, I'm really typically don't rename the variable, so I'm just going to let k be n again. Beautiful. So our job then is to solve this recurrence relation if possible. If not, we can always use it to get so many terms in our series to at least get an approximate solution. Now, so let's just a naught. We don't know what a naught is. We weren't really told, so it could be anything really. So I'm just gonna, a naught is itself, whatever. You can let it be 1 if you make it easier. So according to this recurrence, then a2 is negative 1 over 1 a naught, right? And then we can use this recurrence to then find a4. It's going to be the negative of 1 over 3 times a2. So we just write down what we have. And now here, I'm not going to multiply anything out because I want to see patterns and factors. Okay. Then a6 is negative 1 over 5 times the preceding a4, right? So, and so on. So negative 1 over 7 times the previous thing, which is negative. So looks like we have an alternating sequence here. And so we can guess that if you have an even index, so let's call that, right, if n is equal to an even number, so 2 times some integer, then it looks like the pattern in the denominator, well, first of all, it's alternating, right? So that's going to be negative 1 either to the power k or k minus 1 or something like that. And it looks like it'd just be the power k. How do I know? Well, so a sub 2 should be negative, but a sub 2 is a sub 2 times 1. That's negative, so we want negative 1 to the power 1. Get negative. A sub 4 is the same as a sub 2 times 2, and that's positive, right? So that would make sense that it's negative 1 squared. So it's negative 1 to the power k to account for the alternating character of the sequence. And in the denominator, we have a factorial sort of, right, of just the consecutive odd integers. So we get 1 in the numerator, 1 times 1 times 1, and so on. And this is going to be 2k minus 1, right? So the 7 is 8 minus 1, right? 5 is 6 minus 1, so then 2k minus 3, so on, 2k minus 5, all the way through 1. Now there is a way to write this in terms of something that we can, it's closed, right? There's some, write it in terms of something that's more familiar. So I'll demonstrate what I mean with a sub 8. Notice that we have just product of consecutive odd integers. But if we had a product of all the consecutive integers, period, even and odd, then we get a factorial. So all we're going to do is, I'll just write it like this, 7, 5, 3, 1. And we're just going to simply introduce the factors that we want to see to complete a factorial, as we know. So 6, 4, 2. And since I introduced that in the denominator, I got to introduce those factors in the denominator as well. Okay, and what you want to observe is that since all the factors in the numerator are even, they can be written as 2 times an integer. So 6 is 2 times 3, 4 is 2 times 2, 2 is 2 times 1. The denominator here is 7 factorial. So now we can collect all the factors of 2 and we get 2 cubed. And then we have 3 times 2 times 1 left over. That's just 3 factorial. And so this is kind of what we want to do here. Complete the factorial in the denominator by introducing all the even integers here. So 2k minus 2, 2k minus 4, and so on. All the way through. There's a 2. So we got to introduce those even factors in the numerator as well. So in the denominator, we get 2k minus 1 factorial. So we have a product of consecutive integers there. In the numerator, we can, all the factors are even, so we can factor out, well, we can group all the factors of 2. And how many of them do we have? We'll see in a second. So when you do that, you're going to get 2k minus 1 times, k minus 1, k minus 1, k minus 2, and finally 1. So how many factors did we have? Well, we started with 1, and these are now consecutive integers, and end up with k minus 1. So that's k minus 1 factors. So this would be 2 to the k minus 1. And we'll confirm that that works here. So a sub 8, for example, right? That's 8 is 2 times 4, so k equals 4. And so we should get 2 to the 4 minus 1, 2 cubed. And that's exactly what we see, so it works out. So finally, we have a general formula for the terms of the sequence with an even index, 2 to the k minus 1, k minus 1 factorial, divided by 2k minus 1 factorial. Okay. Well, so that looks like that's going to give us one of the solutions, right? We assume that y. Well, let's actually hold off here. All right. So notice that we are missing all the even index terms. Okay. I'll go ahead and readjust here 1 second. All right. So now we also don't know what A1 is. It's arbitrary, right? We A0 and A1 are based, depend on the initial conditions. You know, for a second order differential equation, we expect two arbitrary constants. So A1 is just whatever. Okay. Now using our recurrence, we can then find A3. Negative 1 over 2, A1. And then find A5 and so on. All the odd indexed terms for a sequence. Okay. So it looks like we can probably come up with a formula for the odd indexed terms. So let's just say, so this should be negative 1 to the k. Is that correct? So a sub 1 is what happens when k is 0. And that should be just a1, right? A3 is what happens when k is 1. And that should be a negative. So it looks like, yeah, negative 1 to the k. That accounts for the alternating part, and then clearly we have 2k minus 2. We're skipping every other integer because it's just the even integers and so on. And that will go all the way to 2. But then you see that we can use that same trick since all the factors in the denominator are even. We can group all the factors of 2 together, be 2 to some power, and then we'd be left with k minus 1, and finally we'll end up with 1. So it looks like there were k factors in the denominator originally, so our power should be 2 to the k here. So now we can finally write this as 2 to the k in the denominator times k factorial a1. Right, so now we have a formula for the even index terms and a formula for the odd index terms. So we accounted for everything. All right, so now we said that our solution, y as a function of x, was this series, but we have different formulas for the even indexed and the odd indexed terms. So I'm just going to write this as k goes from 0 to infinity, and then we're just going to have a sub 2k to account for all the even terms, so to speak, plus, and then k goes from 0 to infinity, and then we're going to have all the odd terms. So we, here we replaced n with 2k, here we replaced n with 2k plus 1. So now we use our formula, and we have a naught as a common factor. Well, I don't recognize that as anything really that in closed form, so let's leave it like that for now at least. Maybe we can use reduction of order if we can figure out what the other term looks like. So here we have a formula for odd index terms. But now this one, an A1 is a common factor, so I'll just pull that out. Now the second series I recognize, right? We recognize that as a, e to the, let's just use theta, I guess. The expansion of the exponential function around 0. So, well, almost. Right? We just have to adjust it a bit. So what we're going to do is notice that we can lump some of the factors together, so we can say that's -1 x squared divided by 2 to the power k. And then we have an extra x left over, and then we're dividing by k factorial. Now that x doesn't involve the index of summation, so I can pull it outside. And then, so like if you compare that to this, that would be like -x squared over 2. So we know that that series converges to an exponential. And if we wanted to, we could maybe possibly log. I doubt that we recognize that anymore. Try reduction of order to find maybe the second solution in closed form, but I'm not going to bother. So there you go. That's our final answer. Example number 2. We're going to find a series solution centered at 0. K is a constant. Assume a series solution. Differentiate a couple times. And then substitute into the differential equation. So we have y double prime plus k squared times x squared times y. So k squared. All right, so now we want to try to get a single series. So the powers of x should be like, or not. So notice that because when n is 0, that's 0. When n is 1, that's 0. The first two terms are 0 anyway. You might as well start the summation at n equals 2. So the first term, we're going to let n equal k minus 2, k plus 2 rather. So we're shifting the index. And of course, if you subtract that over, and we're going to let k equal n again. But we still have a mismatch, right? So what we might have to do is that we can't really shift indices here, or can we? If we let n equal k minus 2, what would happen? Oh, yeah, k, what that choice here, right? N equals, let's say, m minus 2, yeah. Let's see if that would work. Add the 2 over here and just rename n. So n goes from 2 to infinity. So now we have like powers of x, so we're closer to being able to combine these series into a single one. But the index of summation does not start at the same place, right? We have n starts at 0 for the first series, and n equals, so n starts at 2 for the second one. So how can we get these to agree? Well, we're just going to have to pull out the first two terms of this series. So when n is 0, we get a sub 2, 2 times 1, x to the 0. And when n is 1, we get a sub 3, 3 times 2, x. And now we can say that our sum starts at, for the first term at least, starts at 2, goes to infinity. But now we can combine these two into a single series. Beautiful. So now, for our series here to be equal to 0 for all x's, all the coefficients have to be 0. So in particular, a2 has to be 0, and a3 has to be 0. And from over here, all these coefficients have to be 0. For n at least. Interesting there, for n at least 2, right? solve for the highest indexed term of our sequence. And I'm just going to re-index these so that this is a sub n. So that I'm essentially subtracting 2 from each of the n's that I see in this recurrence relation. This is for n at least 4. So now we're going to attempt to try to solve this. I probably could have, let's just see. So a sub naught, we don't know. It's arbitrary. Using our recurrence, notice that we can then solve for A4. And then A8 times the previous stuff, and so on. And then we can solve for A12. And notice that these indices here are 4 apart. So we can write down possibly a general formula for the terms of the sequence that have an index which is a multiple of 4. 0, 4, 8, 12, and so on. So that would be -1 to the k. And here we would get k squared to the power. Fudge. Okay, I can't use k. Silly me. So I'll use m. And that would be k squared to the power m. And this one is a little difficult to fathom, right? What the pattern is, but it's 4m times 4m minus 1 times, and then 4m minus 4, 4m minus 5, and so on. So we get to 4 times 3. So I don't know if that simplifies or not. We can insert some factors that we're missing, 9 and 10. I might just edit this out if it doesn't work out. So, but let's see. So 12, 11, we're missing a 10 and a 9. We have an 8 and a 7. We're missing a 6 and 5. But we have a 4 and 3. Okay, so I'll, of course, introduce those factors in the numerator as well. All right, so let's then use our recurrence relation starting with A1, which is unknown. So A5, B9. So it looks like we're going to have multiples. The index here is always a multiple of 4 plus 1. So that's -1 to the n. K squared to the n. In here it's 4m plus 1 times 4m. And then 4m minus 3, 4m minus 4, dot, 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 all the way through 5 times 4. Now notice that our recurrence relation also tells us that those are the only non-zero, right, multiples when the index is a multiple of 4, or when the index is a multiple of 4 plus 1, then we have non-zero coefficients. But the recurrence relation and the fact that A2 is 0, right, tells us that A6 is 0. And then that tells us that A10 is 0, and so on. So any multiple of 4 plus 2 index is going to give us a coefficient which is 0. And then since A3 is 0, according to the recurrence, A7 is 0, A11 is 0, and so on. A15 is 0. So any term is sequence with an index that's a multiple of 4 plus 3 must be 0. All right. So now we've said that our solution is the series, but we should probably split this up into, well, I'll do it 4. So you're going to have where all the indices are multiples of 4. All the indices are multiple of 4 plus 1, multiple of 4 plus 2, multiples of 4 plus 3. All right, so we're going to go ahead and use that A0 as a common factor. Second term, we're going to use A1 as a common factor. And the other coefficients are 0, so those go out. So there you go. Now, you can find a closed form for these, but you can at least use so many first so many terms here to approximate one. All right, well, that's all I have